Hey everybody, how's it going? So, as I told you, I am going to create a video to help you out with Squeeze Theorem since there weren't many of those questions on our packet. So I'm just going to go over first what the Squeeze Theorem is, and then we're going to do a really easy question and then one that's a lot harder. So we're going to start with just what the Squeeze Theorem is, and it's basically saying that when you're given a function, you're trying to find a limit by using an upper and a lower bound system. We'll go over a lot more about that in just a little bit, but just recognize that you're going to be using bounds. Uh, the hint is that you're only going to use this when everything else fails. So when L'Hopital's rule keeps giving you an indeterminate form, or when you can't simply plug in a number to find an answer, that's when you would use the squeeze theorem. I also want to note that technically the squeeze theorem can be used anytime because all you would do is you would prove that the limit does exist. So technically you can use it whenever you want. However, a lot of times there's a lot simpler ways to get through a problem without having to use it. Also, do not be discouraged if the first time you do the squeeze theorem, it comes out as indeterminate or if you don't get a clear answer, because that might just mean that you picked wrong bounds. And so if you do get something like that, and I can show you an example of what that would look like, just try to redo it and do different bounds, I guess. So the first question that we are going to start with is, hold on one second. All right, so we are going to start with simply problem number 1 here. So that is our limit as x approaches infinity of sine of x over x. And sorry for the horrible handwriting. I do not have very expensive equipment to be doing this. But all right, so let's start by simply plugging it in. We recognize that the x on the denominator would end up being infinity. Okay, but sine of x is going to fluctuate between -1 and 1, right? Just think like, sine of pi over 2 versus sine of 0. And so they're just going to fluctuate. So that means we would end up with negative infinity, or I'm sorry, we would end up with times where we'd have -1 over infinity and then times with 1 over infinity. And we can't get a clear answer whether that's going to be a positive or a negative limit. So what we have to do now is the squeeze theorem. Technically, we could start by doing L'Hopital's. I'm going to leave that up to you if you want to prove that L'Hopital's is just going to give you indeterminate, because technically you would just do the derivative twice and you would end up with a 0 in the denominator, and that would just, you can't divide by 0, so you would end up with does not exist, and that is the wrong answer for this question. So we'll start to do the solution for it. So what we want to start with first is recognizing that sine of x is always going to be greater than or equal to -1, and it's always going to be less than or equal to 1. Think you can never have sine of 2, or sine of any value will never equal 2. That isn't a thing. You can prove that by looking at the graph or using your calculator. So those start to look like our bounds, right? So we have a lower bound that is going to start -1. We have an upper bound at 1. But that is only for sine of x. But if we think about this, what is the only difference between sine of x over x and what we have now? Actually, I'm going to make this x squared, and that's just so that way this is always true. Any value that we plug in for x is always going to be positive. So it will never mess this up. Just because if it was x, which I should not have had there first, so I'm sorry about that. If it was just x, it could be negative, so -1 divided by that negative could become positive, and that just messes everything up. But when we have x squared, it's always going to be positive, so negative divided by that positive is always going to be negative, and the inverse is true for positive. So that keeps our bounds absolutely true at any value. So when we just look at our sine of x over x squared versus what we have started to set up for our bounds, we recognize that all we have to do is divide everything by x squared. So let's do that. Divide absolutely everything by x squared. And I cannot write 2's apparently with this pen. So we end up with -1 over x squared is less than or equal to sine x over x squared, which is less than or equal to 1 over x squared. Now what we do is we just reinstitute our limit. So we write limit as x approaches infinity of 1 over x squared is less than or equal to sine of x over x squared. And actually, I messed up there. It's actually, so that limit is less than the limit as x approaches infinity of sine x over x squared, which is less than or equal to the limit as x approaches infinity of 1 over x squared. And I made a mistake over here on the very first one. I forgot to carry that negative. So yeah, just pay attention. Don't be like me. Anyways, so now we have our squeeze theorem set up where this is our upper bound, which I'm just going to label as UB, and this is our lower bound. Now, what we do is, because we can't figure out what the limit of our actual f of x is, we figure out what the limit of those other two values are. So if you'll just give me a second, I'm going to rewrite all of that because I ran out of space. So limit as x approaches infinity, -1 over x squared, less than equal to that limit of sine x over x squared, which is less than or equal to the same limit of 1 over x squared. All right, so let's take the limit of our lower bound. We recognize that infinity squared, our denominator, is just going to be infinity. So any value over that is just going to end up being 0, right? So we got 0, and then we just rewrite our limit of our f of x because we can't determine it yet. And now the limit of our upper bound. Well, it's pretty much the same exact thing. So we figure out that this is also 0. If a value is greater than or equal to 0, but it's also less than or equal to 0, what does it clearly have to be? Well, of course it has to be 0. So we would end up with limits as x approaches infinity of sine x over x squared is equal to 0. Now to get full credit on your exam, you're also going to have to write by Squeeze Theorem. And so that just takes an extra little step, but sometimes you'll lose points, so please don't forget this. But other than that, that is the main logic, I guess, behind Squeeze Theorem. You just find an upper and lower bound that is easy to solve for the limit, and you essentially squeeze that inner limit, our f of x, we squeeze that until we figure out exactly what it has to be equal to. Now I want to make a quick little side note. If we had ended up solving this limit and figured out, we had 0 is less than our limit, which is less than 5, we can't actually determine what this limit is because it could be 1, it could be 2, it could be 3, it could be 4, you get the point. But that doesn't mean the squeeze theorem doesn't work, it just means we didn't pick our bounds right. So if you get something like this, just go back and try to find your bounds and figure out what went wrong, because you will be able to get a correct squeeze theorem for every equation that is in existence. Some of them are just extremely difficult, so it may take some extra thought. And we're actually going to do a harder one right now.
Solutions to limits using the squeeze principle. Solution 1. First note that $(-1).
Okay, sorry about that. I don't know what happened there. All right, just give me 1 second. I am so disorganized. All right, so this one is pretty crazy. So bear with me as I write it. I will probably make mistakes several times. But I don't want you to panic when you see it, because it does look hard. You probably won't have this hard of a question when you do your test, just because this is really obnoxious. But if you're able to do this question with me, then you can pretty much do any squeeze theorem that's going to be thrown at you. And that includes through Calc 3 and everything, because this will show up again, but that doesn't mean that it's going to be any more difficult. All right, so this is our crazy function. The limit as x approaches infinity of x squared of sine of x plus cosine cubed x all over the quantity, all over the quantities of x squared plus 1 times the quantity of x minus 3. Yeah, you can see that I can't even talk to figure it out. Like I said, you probably won't have the one this hard, but we can figure it out. So let's start by finding the things that we know about. Like last time, we can start to look at sine of x. We know that's going to be less than 1, but greater than -1. We can also look at cosine of x. Now I know it's cosine cubed there, but we're going to first look at cosine of x. That's also less than 1 and greater than -1. Again, that can be proven if you so desire. And what happens when we cube 1 or -1? They just end up exactly the same way. So we get -1 is less than cosine cubed x, which is less than 1. If you weren't able to follow along how I got between these two steps here, then just take x to the power of 3 and figure out what happens when you plug in things like -1 to 1 and things like, 0.2. You'll figure out that this is true. All right. So what we can go on to do is we can figure out that sine of x plus cosine cubed x, that's always going to be greater than -2, but it's always going to be less than 2. Because think about it. At the bare minimum, at the lowest point, we're going to have -1 plus -1, which means we'll have -2. At the absolute maximum of our two values, we're going to have +1 and 1, which means we'll have 2. All right. Now, we can continue on. So we can start by dividing by some things. I am going to go to a new page now. I'm not going to rewrite the function, so if you forget it, please go back and look at it every once in a while or write it down. just because it's a long function, I don't feel like rewriting it, but I will write the start of our bounds down again. All right, now we simply start to shape it exactly the way that our other function was. One of the other parts of our function was x squared. Now, remember that x squared is always going to be positive, so you can multiply it freely and it doesn't change anything. So let's multiply everything by x squared. So that means our negative is going to stay negative and our positive is going to stay positive. So we're good. So we're going to get negative 2 x squared is less than or equal to x squared sine x plus cos cubed of x is less than 2x squared. And yeah, so we're starting. Now, remember we had some things on the denominator. One of the things that we had was x minus 3. Technically, that 1 can go to negative, so it could mess it up. But because we're going to limit as x approaches infinity, that means infinity minus 3 is going to be a positive number. So we're just dividing by positive numbers on the both sides, so we don't mess anything up. So now we can divide everything by x minus 3. So we end up with negative 2 x squared over x minus 3 is less than or equal to x squared sine x plus cos cubed x all over x minus 3, which is less than or equal to 2x squared over x minus 3. And you might be able to guess what our next step is. Again, I'm not going to rewrite everything, but take quick snapshot if you need to. I will rewrite our start of our bounds here. All right. Sorry, I forgot what it was already. Oh my gosh. All right. There we go. Okay. Now, like I said, you can probably guess what we're going to do next. Our next thing that we had was another function on our denominator. So we can multiply everything. And sorry that I'm going to write it down on the side. You should never do that, but can't really expand my computer screen. So our other part was to multiply it by 1 over x squared plus 1. Yes, that's what it was. So 1 over x squared plus 1 is what we're going to multiply everything by. So when we do that, we end up with negative 2 x squared over x squared plus 1 x minus 3, which is less than or equal to x squared sine x minus cos cubed x over x squared plus 1 x minus 3, which is less than or equal to 2x squared for x minus 3 x squared plus 1. Now, we have our function f of x. And that means this is our upper bound, and this here is our lower bound. It was a very long process to get there, and like I said, I don't expect anything that's difficult on your tests. But all it is just recognizing these patterns of positive numbers and that when you divide negative numbers by them, they stay negative, and uh, the same logic for the positive numbers. The hardest thing is always finding that initial starting point. Being able to think through that sine x minus cosine cubed, or sine x plus cosine cubed x. Sorry if I've been writing that for a while. It's positive there. I hope I have not messed anyone up. I just realized that, so I apologize for that. But sine x plus cosine cubed x is going to equal -2 up to 2. And so that was something that you have to think through, but it's something that we know. And so we can do that. All right. So I'm not going to write all of this again, meaning all of this. I keep pointing to stuff like I'm in class and I realize that you guys can't see me. So, all right. I'm not going to rewrite all of this because it's obnoxiously long, but I'm going to take the limit of all of these things. And what we're going to figure out is that we have a -2x squared over something with an x cubed in it because we got x times x, which means that the limit as x approaches infinity, this is going to go to 0. And that was one of our beginning limit rules. So, feel free to ask me if you have any questions about that. But, I'm not going to spend time going over it right now. Anyways, so this would go to 0 because you have some value times x squared over x cubed plus a whole bunch of other stuff that we don't care about. So we end up with essentially all that's everything simplifies down into -2 over x. What's the limit as x approaches infinity of that? Well, it's just 0. And the same thing happens over here, except now we have +2 over it. But it still just approaches 0. So what we figure out is that 0 is less than our limit, less than or equal to our limit, which is less than or equal to 0. And again, that just proves that the limits as x approaches infinity, and I'm just writing it as f of x because I'm way too lazy to rewrite everything, is equal to 0. And again, write down by Squeeze Theorem. And that's it. We went from some crazy problem that is so scary to 0 in I don't know how long, but it was a pretty short time. Again, your hardest part is going to be finding your upper bound and lower bound. Always look for things that you know are going to be true, such as something squared is always positive. That says positive, I cannot write. And also that sine or cosine is going to be -1 to 1. There are other things that you'll have to look for, but you should be able to figure them out. So again, just finding your upper and lower bounds, setting everything up to make sure that it's true until you get to your original function, and then taking the limit of everything. And what you do is you just squeeze your limit hardcore right in between until you prove that it has to be 0 because everything above it and everything below it is 0. So there's no way it isn't 0. All right, so that is Squeeze Theorem. Feel free to ask me any questions that you may have. And, but yeah, I guess I don't know where I was going with that sentence. Yeah, so ask me any questions that you may have. And also let me know if this video was instructive, because if you liked it, I can keep making these videos. I enjoy doing it, but they do take a lot of time. So if you absolutely hated it and this helped you none, please let me know so that way I don't keep making them. Either way, you won't hurt my feelings. I just want to hear honest feedback. So I do actually hope that this helped you. I wouldn't be making it if I wasn't hoping that. That being said, I'm gonna end it. So I will see you all in class. All right. See ya.